So what does it really take to make a robot move with almost unbelievable precision? In this explainer, we're going to do something a little different. We're going to reverse engineer a high-performance robotics project, piece by piece, to see exactly how it pulls off these near-perfect results. And you know what? We're going to start at the end, with the final numbers.
Okay, check this out. This is our final destination, a robot arm drawing a 10-centimeter square. Now look at those numbers. The average error, the root mean square error, across that entire path is just 0.008 of a millimeter. To give you some perspective, a single human hair is about 10 times thicker than that. This isn't just precise, it's practically microscopic.
Yeah, let that number sink in for a second. 0.008 millimeters. Now, getting that kind of accuracy from a custom software stack, even in a simulator, is a huge deal. This is what separates a simple hobby robot from a genuine high-performance machine that could do something like, say, delicate assembly or even surgery.
So, that leads us right to the big question for this whole thing. How on earth do you do it? How do you command a hunk of metal and motors to follow a perfect digital line with almost zero error? Well, that's exactly what we're about to deconstruct.
All right, first things first. Before a robot can do anything, it needs to understand our world. It needs a kind of dictionary, a way to translate between the world of X and Y coordinates that we understand and the robot's world, which is all about its own joint angles.
And that dictionary has two sides to it. On one side, you have forward kinematics, or FK. This basically answers the question, if my joints are at these specific angles, where is my hand? Simple enough. But the other side, inverse kinematics, or IK, answers the question we usually care about. Okay, I want to put my hand here. What angles do my joints need to be at? You absolutely have to be fluent in both to control any serious robot arm.
But here's the thing. Once you've written the code for something like forward kinematics, how do you know you got the math right? You can't just cross your fingers and hope for the best. The proper engineering way is cross-validation. You take your result and you check it against a completely independent, trusted source. For this project, that trusted source was the MuJoCo physics engine itself, which has its own built-in kinematics.
And bam! This is the result of that process. We ran our custom math against MuJoCo's internal solver for a bunch of different joint positions. And look at that error, 0. A perfect match, all the way down to the 6th decimal place. Getting this confirmation was huge. It meant we had a rock-solid foundation to build everything else on top of.
Okay, so our kinematics are sorted. We can now tell the robot where to put its hand. But that's only half the battle. We also have to tell it how to get there. You can't just tell it to teleport from point A to point B. That's not smooth, and it's definitely not precise. You need a plan, a trajectory.
Now, for a high-precision path, a simple straight line just won't cut it. This project uses something called a quintic trajectory. And the reason this is so important is that while a simpler plan might make sure the robot starts and stops with zero velocity, a quintic plan goes one better. It also makes sure there's zero acceleration at the beginning and end. And that's the key to getting rid of any jerkiness, which is absolutely critical for this kind of work.
All right, so we have our destination from IK, and we have a super smooth path from our trajectory planner. Now we need the engine. We need the brains of the operation that's actually going to execute the plan and stomp out any errors the moment they appear. This is the job of the control law.
And this is the secret sauce of this whole project. It uses a method called computed torque control. You see, most simple controllers just react to errors after they've already happened. This one is different. It's proactive. It uses a math model of the robot's own physics, its inertia, its gravity, to predict and cancel out those forces before they can even cause an error. It's kind of like wearing noise-canceling headphones for physics. And that is how you get that sub-millimeter precision. So, let's just walk through the whole pipeline one more time. First, path planning creates that smooth quintic profile. Then, for every single point on that path, inverse kinematics figures out the target joint angles. A tool called the Jacobian then helps us figure out how fast each joint needs to move. And finally, all of that gets fed into the computed torque controller, which spits out the exact motor torques we need. See how each step just flows into the next? But of course, no project this complex works perfectly the first time, right? The journey from a great idea on a whiteboard to a working simulation is always paved with bugs. And honestly, understanding the bugs is just as important as understanding the theory.
So the first big one was a classic. You're going to laugh. In the robot's model file, the joint limits were being interpreted in degrees, But all of our math was being done in radians, so the poor robot thought its limit was just a couple of degrees instead of, 180. The controller would hit this invisible wall and just freak out. The fix? Changing a single word in the file to radian. Hours of debugging for one word.
The next bug was even sneakier. The robot model had this nice-looking base, right? Just for looks, but we forgot to tell the physics engine that it was just for decoration. So, as the arm moved, the simulation thought it was constantly crashing into its own base, which created these huge, completely fake forces that sent the controller into a tailspin. The fix was just to mark all the cosmetic parts as non-collidable. And finally, we ran into a textbook robotics problem. For any given point in space, there are often two ways for the arm to reach it, an elbow-up pose and an elbow-down pose. Our IK solver was trying to be clever and pick the one with the smallest joint movement, but sometimes that meant picking an elbow-up pose that would actually make the arm collide with itself. So we made a simple but crucial fix. We just told the solver to always prefer the elbow-down solution. Problem solved. Predictability is key.
So when you pull all of this together, the fundamental math, the path planning, the advanced control, and all the bug fixes, what you get is a complete end-to-end robotic software stack. Every single piece has a critical job to do, and they all have to work together perfectly.
And this table really lays out those key pieces nicely. Inverse kinematics was our translator. The trajectory generator was our smooth path planner. The Jacobian was our velocity converter. And it all led to the computed torque law, that proactive engine that really drove the whole thing home. It's a full system for turning a high-level goal into low-level motor commands.
At the end of the day, drawing a perfect square is just a benchmark, right? But the principles we've covered here, the kinematics, the trajectory planning, the physics-based control, these are the building blocks for just about any advanced robot, from a surgical assistant to a factory arm. A system that can do this has unlocked a world of potential. So the only real question left is, what would you do with it?